Part 2 of depositional sequence will see what we have talked about in the first part. We understand seismic and well log are integrated to study sequence stratigraphy. Sequence stratigraphy analyzes the sedimentary response to changes in base level and deposition trend that emerges from the interplay of accommodation and sedimentation. Sequence stratigraphy has tremendous potential to decipher the Earth's geological record of local global changes and to improve prediction of economic hydrocarbon exploration and production. System track is an important concept which includes all strata accumulated across the basin during a particular stage of shoreline shift. Sequence is a relatively conformable succession of genetically related strata bounded by unconformities or their correlative conformities. Angular unconformity is an unconformity between two groups of rocks whose bedding planes are not parallel or in which the older underlying rocks dip at different angles than the younger underlying strata. The next concept is nonconformity, an unconformity developed between sedimentary rocks and the older igneous or metamorphic rocks that had been exposed to erosion before the overlying sediment covered them. Conformity is no hiatus. There are two more concepts which are interesting to understand: disconformity and paraconformity. In disconformity and unconformity, in which bedding plane above and below the break are essentially parallel, indicating a significant interruption in the overlying sequence of sedimentary rocks. Paraconformity is an obscure and uncertain unconformity in which no erosion surface is desimable and in which the beds above and below the break are parallel. In the next slide, we can see that how we have identified the paraconformity with the red line in the outcrop. We can also see in figure B that there is a change from A to B, wave-dominated shallow marine succession, showing the transition between gradational-based A and sharp-based upper shore face force-regressive phases. It also talks that in this diagram, wave-dominated shallow marine succession can be observed in the outcrop, which are also reflected in the seismic section when we try to interpret the acoustic impedance boundaries, and also the surfaces which is marked in red, which can be seen in outcrop, mimics in the subsurface also on the seismic section. This is a very important understanding of stages of shore face. We can see in this the shore face is actually can be divided in three different formation, three different time. One is the onset of force regression, where we can see that we from the fluvial coastal plain we have the shore face, the inner shelf and the outer shelf. The inner shelf and the outer shelf is between two windows, which is the fair weather window and also which is the stormy window. In between there is a scouring and we can see the hammocky clinoform, whereas in the case of shore face we can see the cross stratification. As we go into the ongoing force regression, end of time step 1, we can see that the inner shelf has prolonged and we can see that hammocks can be seen at the end of the inner shell. We can also see the stiff-faced erosional surface on the fluvial coastal plain, and we have seen the clinoform developing, that is 1 and 2. The clinoform goes on developing 1, 2 and 3. These are mostly gradational in nature, and as we go to the shore face to the inner shelf, we can see the outer shelf is missing, and we can see the dumps which are the canyon fields. There is a cut little bit in the inner shelf and then there is the dump. The subaerial unconformity is marked by red, and when we can see the HST and the force regressive clinoforms which are developing. The blue color, that is the light blue, talks about the force regressive surface deposit, whereas the dark color talks of the force regressive shelf deposit, and we can see by the anti-clockwise arrow the wave erosion in the lower shore face. As we go into the next slide, we can see the architecture of the sequence stratigraphic stages in wave-bound dominated shallow marine setting, we can see that there are vertical stratification which has been taken from A, B, C, D, E, and F. In A, B, and C, we can see it is non-marine, and in D, E, F, it is talking about the shore face and the shelf. In all the cases, we can see one thing, that it is easy to understand the maximum flooding surface, and we can see that the coarsening happens in the right hand side. So at the case of TST, we can see a fining upward sequence. As we go to the maximum flooding surface and then move into the HST, we get the progradational features. It can be marine in nature, and in case of the inner shell, that is the case where we have the marine, and when we have the marine in figure A, B, and C, we can still see in the HST there is a coarsening upward sequence. After that, there is the coarsening upward is limited, and we see that it is more monotonous. Whereas in case of the marine sequence, we can see the TST, HST, and also the LST in all the three cases, and we first see a fining upward sequence, and then we see a coarsening upward sequence. So that is more or less the architecture of the sequence stratigraphic surface in wave dominated shallow marine setting, which helps to understand how the inner shelf will look like, how the shore face will look like, and how the coastal plain will look like in case of vertical stratification, which has taken here to understand how the response are. In case of wave log expression of basal surface, we understand that it is a very important example to understand that well logs plays a very important understanding on the basal surface. Well log also gives a very important understanding on the maximum flooding surface. The maximum flooding surface is also defined relative to the transgressive regressive curve, which marks the end of shoreline transgression, and hence the surface separates retrograding strata below from the prograding strata above. The presence of prograding strata above identifies the maximum flooding surface as a downlap surface on seismic data. The change from the retrogradational to overlying progradational stacking pattern take place during base level rise at the shoreline when sedimentation rate starts to outspace the rate of base level rise. The maximum flooding surface is generally conformable excepting for the outer shell and outer slope region. Maximum flooding surface are arguably the easiest stratigraphic marker to be used for subdivision of stratigraphic succession, especially in marine to coastal plain setting, because they are the heart of aerially extensive condensation which form the shoreline and when the shoreline reaches maximum landward position. They also tend to exhibit a high gamma ray response. So if you see the gamma rays here, whether they are taken from the shore face or whether they are taken for the shelf, we can see the change in gamma ray. When there is a gamma rays moves towards the left, it is mostly we can see the gradational type of shore face, whereas it is sharp faced in case of the shelf. However, we can see the sandy faces in the case of between the HST and the LST, and the reverse happens mostly on the top, where on the right side, that is on the faces we can see on the shelf, we can see that it is more pelagic, and we can see a gamma ray surge which is a box shaped gamma ray, and that is helps us to identify that the gamma ray is from the deep marine sequence. So these are some of the information which should be kept in mind when we take examples from the log to understand how the basal surfaces will look like. We take the well log expression of regressive surface. The sharp base shore face deposits a thicker base inward relative to the seaward termination of the subaerial unconformity, as they include force regressive and low stand normal regressive strata. Log examples are taken to make people understand where we should get in gamma ray the LST, which is the low stand system track, the FSST, which is the falling stage system track, and HST. We can see once again the shallow marine cases which has been taken, and we have seen that in case of gamma ray, when there is a low gamma ray, which is more or less giving an understanding of the shore base and also giving an understanding of the clastic sediment, the sonic phases, if you see, has a very high velocity. So if we study the P wave velocity vis-a-vis the gamma ray, we can understand the break, where is the FSST and where is the base of the LST. This is true whether we take a deep marine case or a shallow marine case, and here are certain examples to show where the break starts and what is the division between the LST and the FFST. So sharp base shore face are important to understand in the shallow marine case, and also if you have a sonic log, please look into that in order to understand what is the behavior of the sonic log, where it is more monotonous, where there are changes in the sonic log over a very small space, and where there is a sharp change in the sonic log. We can also see in this diagram the deep-oriented stratigraphic cross-section through fluvial to estuarine succession in wave and type dominating settings. We can see here that what happens in the marine section and what happens to more on the incised canyons what we see on the wave dominated section. If you see the LST, the canyons both in the wave dominated and in the tide dominated are very much elongated, and they are not connected to each other. They are connected to each other. Whereas in case of the TST, they are isolated pockets. They are the fans which we identify on the seismic, but these fans are more isolated fans. These fans are the canyons or the cut and fill structure which are easily identifiable on the seismic, and also the boundary between the LST and HST, LST and the TST need to be identified in the seismic to understand the central Uchuri region and more the isolated meandering channel and the amalgamated channel fields, which are the braided channel fields in the LST, and the isolated one is mostly on the TST. The well log expression of the maximum flooding surface has been talked about. Well log expression of the maximum flooding surface talks about that wherever there is a maximum flooding surface, it is an organic rich environment. There is a lot of gamma ray response, and the gamma ray is peaking in this case. The gamma ray may be a sharp change or maybe a box shape change, where we can see that presence of thorium, uranium and potassium is there, and if you do a test at the maximum flooding surface, it gives an identity to differentiate between the regions in order to see where the prograding amalgamations are taking place and where are the aggradation. In this seismic section, we explain what we are talking about. We can easily identify the MFS with the blue dotted line, and above that we can see the base lap, that is the down lap we can see, and we can see the progradational sequence which are there. The progradational sequence are marked with red, which is the high stand system track delta. Below the MFS we have the TST shell, and these are very common in case of KG and Kaveri basin, where in the deep setup we can see these progradational features happening, and if we are lucky, these are hydrocarbon bearing, and on the seismic we should be able to make a display in the 3D in order to understand the movement of the progradation. That's all for today, and as we end, we can also see that how should the transgressive strata looks like, and we can see the shell-fell transgressive wedge which is there and deep water transgressive wedge. The shell-fell transgressive wedge is thin in nature, whereas the marine on-lap TST is mostly hummocky in nature, where the basal surface is of different material, and because of the movement of water and sediment supply and the density which is there in the materials which are moving, the coarser grain is at the bottom and the finer grain is on the top. With this, we come to the end of the second part of the depositional sequence.